Okay, so we've learned about correlation, which is R. We've learned about regression, which is finding that line of best fit, the least squares regression line. And we know that these are ways to describe relationships between two quantitative variables. Okay? So this is all great, but we have to be aware of some things so we're sure that we don't misuse it. So one would be careful about distinguishing between the explanatory and response variables. Sometimes we've talked about that there isn't really a distinction, but just be sure that in that case that you can explain what you did. I use this as my explanatory variable, I use this as my response variable. If one variable does seem to explain the other in some way, then make sure that you make that the explanatory variable. But once you've done that, it's important to note that even if you switch them, it will make a difference in regression. It's going to change your line. Okay, so if you change explanatory and response variable, the line will change. However, okay, so here's that example. And we see, just like when we watched, when we looked at this data before with the trucks, with how far they've been driven and how much they were costing, if they switch that and put price as the explanatory variable and miles as the response variable, then if you look at those equations that's shown in the boxes, they have definitely changed. The y-intercept is different, the slope is different, s is different, r squared is different. Well, I'm sorry, r squared is the same, okay? So be aware that that's going to affect them. So, you know, in those cases where it's hard to tell which one's which, you might do one thing, your friend might do the other, and you might look at your lines and say, hey, they're different, and that's right, they will be. Second of all, and I should maybe have pointed out, r squared did not change. When the equations changed, r squared did not change. So correlation doesn't change, but regression does. So in this, if you look at these four graphs, they look like four extremely different graphs, okay? So what's the same about them? Well, if you look at the horizontal axes are pretty much the same. The vertical axes have some difference, not huge difference, but some difference. But what else is the same? Well, the R for each one of these is identical. But notice how the first one, A, is, you know, pretty much linear. We would look at that and say that looks pretty linear. We look at B, not at all linear. It's a curve. You look at C and you say, man, that's almost perfectly linear, except for this one outlier up there. And then look at D, and here's all these vertical plots at 8, and one point way over there at 18. And yet they all have the same R, the same correlation. Well, in addition to that, if we were to do a linear regression, all of them would have the exact same line describing them as their prediction line. So obviously, you have to be very careful to only use correlation and regression when it is a linear relationship. That line would not describe graph B. That line would not describe graph D. And graph C, it would describe, but there's probably even a better line if we were to ignore the outlier. So if you were a statistician, you would probably look and see, well, what is this odd point? You know, it would depend on what your data was. And depending on what you were studying and what that point was, you might say, oh, that point's a mistake. Or maybe it's genuinely an outlier. But as far as predicting the next point, I think I would want to use the line that doesn't include that outlier, because I doubt that the next point would be an outlier like that one. Okay. So then here's another example, and it says correlation and least squares regression lines are not resistant. So this is kind of interesting. So here's a graph along the horizontal axis. We see they've recorded the age that an infant was when they said their first word. And then this is related to something called their Gessel score, which honestly I don't know anything about, but it's obviously some score about that has to do with early childhood and their learning, I would suspect. So we see the least squares regression line there. And now we see if they've taken that same data and they've redone those regression lines by leaving out these outliers. So we've got child 18 down here as an outlier. Our original line, which is the green one, is the original least squares regression line. If they leave out child 18, which is this one down here, then look how much the line is altered. It's very, very different. And if we look up here at the equations, we see with all the children, there's the R, there's the prediction line. If we look without child 18, the R is very different, much smaller, correlation is much weaker, and the prediction line is much changed. The y-intercept is different, and the slope is certainly very different. Now, if we take out child 19, but leave in child 18, but take out child 19 up here, then the red line is the line of prediction. Notice how close the red line is to the green line. So without child 19, the R is not that much different from the original line, and the y-intercept is very close to the same, and the slope is very close to the same. So child 19 had very little effect on the least squared regression line and on R, whereas child 18 had a lot of effect. So we see that a horizontally situated outlier is going to have more effect on changing the least squared regression line than the vertical outlier. So we say it's not resistant because it is affected by outlier. And then the point that causes this great change, which was child 18 on the last slide, we call that point influential. So an outlier, we know, is an observation that lies outside the overall pattern. Obviously, I'm doing this at school. And we know what outliers are, so that's good. And then it tells us that points that are outliers in the y direction, so up and down, but not in the x direction, have large residuals. Other outliers might not have large residuals. So on the x-axis, if there's a horizontal outlier, it might not have a large residual. An observation is influential if by removing it, it would markedly change the result of the calculation. So by taking it out, would it greatly change that line? And if it would, then we say it is influential. So here's our summary of this section. It goes right along with what's on your sheet that I gave you at the beginning of the unit that shows all of the targets for this unit. And so get to work hard this class period and try to get all that homework done. Work together, help each other. Okay, bye-bye.